In this video, we're going to continue our study of square roots. We're going to take a look at irrational square roots this time. So we'll talk about what the difference between these types of square roots and the ones we previously discussed. We'll do that right here at the beginning. So our objective this time is to simplify square roots that do not represent a rational number. So your last assignment, all the square roots that you worked with, they all represented rational numbers. So when you simplified them, you always got a rational number for your final result. And this time around, that won't happen. So let's talk about what the difference between them is. So not all positive real numbers have square roots that are rational. So let's start with one we looked at last time. So if you were asked to find the positive or principal square root of 49, well, hopefully you would recognize that 49 is a perfect square. So since it's a perfect square, we can write this as, instead of 49, we can write it as 7 squared. So since 7 squared gives us 49, the definition of a square root says that its positive square root is 7. So the positive square root of 49 is 7. So what we just found out there is the principal square root, or positive square root, of 49 is positive 7. Now that's what we did last time. Now the reason we start with those is when we simplify it, we get numbers like 7, which are rational numbers. Okay, so 7 is a rational number. And the reason we know that is 7 is exactly the same thing as 7 over 1. So the number 7 can be written as a fraction where the numerator and the denominator are both integers. So this is an integer and this is an integer. So the number 7 can also be written as 7 over 1, where both the numerator and denominator are integers. And recall that integers are all the positive and negative whole numbers and also 0. So these kinds of numbers, these are all integers. So if you can take two of those numbers and make a fraction, you get a rational number. And remember, it's called a rational number because you're making a ratio. So 7 compared to 1, that's a ratio. So when you make a ratio of integers, you get a rational number. So every single square root that you dealt with last time, the result was a rational number, one of these kinds of numbers. But that won't always be the case. So let's say you had the square root, the principal square root of 3. Well, 3 is not a perfect square. So 3 is not a perfect square. Actually, 3 is a prime number. 3 is a prime number. So 3, I can only split that up into 1 times 3. So even if I try to use my property and split these up, principal square root of 1, principal square root of 3, well, 1 is a perfect square. 1's a perfect square. So the principal square root of 1 is just 1. So even if I try to simplify this, so 3 breaks up into 1 and 3, that's it. Those are the only two numbers that multiply together to give me 3. It's a perfect square. Even if I try to split this up, I just end up with the same thing I started with, the principal square root of 3. So I don't actually ever get a rational number. I just end up back with this square root of 3. So this, the square root of 3, this is not a rational number. Now, how do I know that? Well, there are proofs that prove that this is irrational. I'm not going to go into that um, right now. If we actually were meeting in class under normal conditions, I actually probably would walk you through the proof that the square root of 2 is irrational, just so you can kind of see how we really actually know that this is not rational. But for now, just realize that the square root of 3, you cannot write it as one integer divided by another integer. So no matter which two integers you grab from the list of, this giant never-ending list of an infinite amount of integers, no matter which two that you grab and try to divide them, you would never get the square root of 3. So for now, that's all I'm going to say on the subject, because the proof itself is kind of lengthy and it's different for different numbers, or at least the proofs I'm familiar with. So, but the square root of 3 is not a rational number. It's just, you just get the principal square root of 3. So, um, but you're thinking, okay, square root of 3, what good is that number? What if I have to do a measurement and my measurement involves the square root of 3? How would I measure that? Well, nowadays we have technology, so we can use a calculator to get an approximation for that number. So we can get an idea of where that number would be on the number line using technology, using a calculator. Now, prior to calculators, there were other methods to get these approximations, but for now we have calculators that'll do it for us. So um, if you get your calculator out, so here's a calculator here, and I ask it for the square root of 3, um, it'll give me a decimal approximation. Now, depending on how your calculator is set up, it'll give you more decimals than this or less decimals than this, but it'll give you some sort of decimal approximation. Okay, so um, the square root of 3, it turns out it's approximately 1.732050 80757, and then this will just keep going. So it turns out the square root of 3 is closer to 2 on the number line than it is to 1. It's a little bit past 1.5 on a number line. So what's important though is this decimal goes on forever with no pattern. So if we had a calculator that could give us 1,000 decimal places, we would get 1,000 decimal places, and when you looked at them, you'd see no discernible pattern. There'd be no repeating pattern. Um, you would just see what appear to be kind of random numbers. Now, they're not random. You can obtain them by division, um, which we're not going to do. That's not the purpose of this lesson. But just know that these irrational numbers, you can get a decimal approximation for them using a calculator. And then depending on how your calculator is set up, you can get a bunch of decimals or just a few decimals. But usually if you're going to do measurements with these kind of numbers, just having a few decimal places is enough. So knowing that square root of 3 is about 1.7 um, is usually good enough when you're doing measurements that end up involving such numbers. So some of these irrational numbers can be simplified. Now I just showed you one that can't. So the square root of 3, I tried to simplify it, and all I just kept getting, I got square root of 3 again. It didn't really get me anywhere. But some of them actually can be simplified, and that's what we're going to practice today. That's actually what this lesson is about. So for example, let's say you had the principal square root of 50. 50. So the first thing we would want to notice is this is not a perfect square. This is not a perfect square. It's close. 49 is a perfect square, um, but it's not a perfect square. So as soon as we recognize that it's not a perfect square, that's how we know that we can try to simplify it. And sometimes they can be simplified and sometimes they can't. Um, So this one, it turns out, can be simplified. Now, how do I know? Well, that's what we're gonna practice. Is I'm basically gonna look at that number and ask myself, are there any perfect squares that would divide into 50 without a remainder? So in my big giant list of perfect squares, are any of those numbers that would go into 50 um, evenly or without a remainder? And it turns out there is, the number 25. So 25 goes into 50 two times. So that's a goofy looking two. So I can rewrite 50, instead of writing 50, I can change it to 25 times 2, which is perfectly legal because 25 times 2 is 50. Those are equal. So I can replace 50 with 25 times 2. And then as we know from our last lesson, I can split that up into 2 principal square roots. And 25 is a perfect square. So this is a perfect square. And that's useful because the principal square root of 25 is 5. And then I get principal square root of 2. Well, 2 is prime. 2 is a prime number. So there are no perfect squares other than positive 1 that go into 2 evenly with no remainder. So that's as far as I can go. I can't break 2 up into any other useful numbers that have a perfect square other than 1. So I would stop here. So it turns out the principal square root of 50 is actually the same thing as 5 times the principal square root of 2. Those are exactly the same number and would represent the same location on a number line. And if I wanted a decimal for that, I could get a calculator out and get a decimal for that. Um, so if we were curious what decimal that is, I would just do 5 times the square root of 2. And it turns out it's a little bit more than 7. So 7.07. If I really wanted to know where that was at on a number line. So, but we kind of could have guessed that. Um, we know that the square root of 49 is 7. Whoops. We know that the square root of 49 is 7. So the square root of 50 is going to be bigger than 7 because 49 is smaller than 50. 50 is bigger than 49. So, um, but 49 and 50 are not that far apart. So the square root of 50 is going to be um, bigger than 7, but really close to 7. And sure enough, the calculator tells me it's 7.07, which is really close to 7, but a little bit bigger. So we could have guessed that that number was a little bit bigger than 7, but the calculator is always going to give us a more accurate approximation. Okay, so what we're actually going to practice is simplifying numbers like that. Okay, um, so to simplify a square root, we're going to do exactly what we did up here. We're going to look for the biggest perfect square that goes in with no remainder, then we're going to split it up, and then we're going to use our perfect squares to get our final answer. So the first thing we want to do is we want to divide I'm going to use a new word here, but we'll write down what it is. We're going to divide the radicand by perfect squares until we find the biggest perfect square that isn't positive 1, right? Because positive 1 is not useful. That goes in with no remainder. that goes in with no remainder. Now I used a new word here, used a word called radicand. So what is the radicand? The radicand is the number under the square root sign. So we're going to get a little bit of vocab here, nothing crazy. So this is called the radicand. And then this symbol, we keep calling it the square root symbol, but it actually has a better name. This is called a radical sign. So that's called a radical sign, and then the number under it is called the radicand. So we're going to divide the radicand by perfect squares until we find the biggest perfect square that isn't positive 1 that goes in with no remainder. Well, after we find it, if we do find one, because as we know, you won't always get one. Things like square root of 3 didn't simplify. Square root of 2 didn't simplify. But if you do find one, we're going to write the radicand as factors. And then we're going to use our property that we talked about in the last assignment, last set of notes, where you split up your square roots. And then we are going to simplify the radical containing the perfect square. So you've seen one already. We'll do some more examples, but you'll see one. You've seen one already right here. So you basically take 50. So we just, for this one earlier, we took 50. We divided it by 25, because 25 is the biggest perfect square that goes in evenly, and we get 2. So 25 times 2 gives us 50. Then we split up the square roots into 2 square roots, and then this one had the perfect square. So instead of principal square root of 25, we wrote 5, which is what we practiced in the last homework. So that's what we're going to do. So when you do this homework, make sure you have your list of perfect squares out from the last set of notes. So that list of perfect squares is very helpful. So if you go back in our last set of notes, we had a list of perfect squares. So here they are. I, of course, doodled on it when I was making that video, but this list of perfect squares is going to come in handy. So 0, 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. Now, a couple of these we can ignore. We don't care about. This one and this one are not going to prove useful. So really, you're just going to be thinking about 4, 9, 16, 25, 36, all the way out to, you know, hopefully we won't need these bigger ones very often, but we might. We might. We have calculators to help us with that division. So we're going to use that list. All right, so let's give this a try. So for example, let's simplify some square roots here. So our first one, let's say you had the principal square root of 75. 75. Now, don't waste your time. Be smart about this. 75 is an odd number, and it ends in 5. So there's no reason to check and see if 4, remember 4 is a perfect square, there's no reason to check if 4 is going to go in evenly. It won't. Why would it? 75 is an odd number, so 4 is not going to go in there. Now, since it ends in a 5, really that narrows things down. The only thing that goes into numbers that end in 5, the only types of numbers that go in evenly are things that end in 5 or 0. So the very first one we should check is 25. 25 is a perfect square, and it ends in 5. So there's a high probability that this will go in with no remainder. And sure enough, it goes in 3 times. and 3 is prime, so that's going to be our biggest. So we can break this up into 25 times 3. Then we can use our property, split up the square roots. And the principal square root of 25 is 5, and 3 is prime, so that's not going to simplify anymore. Let's try another one. Let's say we had 6 times the square root, principal square root of 112. Well, our job is to simplify this, the radical, the grouping symbol. So I don't really care about this 6. The 6 is just going to sit there. It's not bothering anything. Order of operations says I got to do the grouping symbol first, and the grouping symbol is the radical. So I have 112. Well, 112 is not a perfect square. That's not in our list of perfect squares. And notice that it is even. It is even. So I only need to divide by even perfect squares. So, I mean, you can go through your list, but there's going to be some of them that you're just kind of wasting your time. So 112, the first perfect square I would check is 4. And 4 does go in. But remember, I want the biggest perfect square. So I don't need to check 9. 9 is a perfect square, but it's an odd number. It's an odd number. So odd numbers aren't going to go into even numbers without a remainder. So the next one I would check after 9, even though I wouldn't have checked 9, is 16. Because 16 is a perfect square and it's even. And notice it goes in 7 times, and 7 is a prime number. So that's going to be the biggest perfect square that goes in with no remainder. So this is going to be 16 times 7. So 112 breaks up into 16 times 7. So I'm going to leave the 6 alone. I'm going to use my property for square roots that we used that we learned about in the last section. I'm going to leave that 6 alone. It's not doing anything. Principal square root of 16 is 4. And now I'm done with the grouping symbols because I can't simplify the square root of 7. 7's prime. So now I'm going to multiply from left to right. So 6 times 4 is 24. And I'm done. I don't want a decimal. The directions weren't to get a decimal. It was just to simplify the square root. So notice this 6 that's out front, it didn't really do anything until the very end when I was allowed to finally multiply some things left to right. Next up, let's try principal square root of 891. 891. Now, notice it's an odd number. It's an odd number. So don't bother dividing by the even perfect squares. There's no reason to. So 891, I'm not going to divide it by 4. That'd be a waste of time. 4 is an even number. So 891 divided by 9, ooh, that worked. That worked. But that might not be the biggest perfect square. I want the biggest perfect square. So 891 divided by, well, I'm not going to do 16. 16 is even, so that'd be a waste of time. 25 won't work because the last digit is a 1, so 25 is not going to go in evenly. 36, nope, it's even. 40, ooh, let's try 49. Oh, 49 didn't work. It had a remainder. Let's try, whoops. 64 is even, so I don't want to try that one. Ooh, how about 81? Oh, look at that. 81 went in with no remainder, and 11 is prime. So I think we found the biggest. So this is going to be 81 times 11. We'll split up our square roots. Principal square root of 81 is 9. So we get 9 times the principal square root of 11. 11 is prime, so we can't simplify that anymore. Let's try one more. What if we had 3 times the principal square root of 684? So the 3 out front, as we saw earlier, is just going to mind its own business until we actually have something to multiply it with. Or another way to think of it is when we're done with the grouping symbols. So 684, notice it ends in a 4, so it's even. So the first thing I would try is 4, because 4 is an even valued perfect square. And it worked. It went in with no remainder, but it might not be the biggest. Might not be the biggest. So I wouldn't divide by 9 because 9 is odd. So I'm not going to check 9. 16. Let's try 16. Nope. Let's try, let's see, 25 won't work. 36. That's an even perfect square. 19. 19 is a prime number. So I think we just found the biggest. So this is going to be 36 times 19. Split up the square roots. Principal square root of 36 is 6. And now we can actually multiply and get 18 times the principal square root of 19. 19 is prime, so it's not going to simplify. So this is what you're going to practice in this week's homework is you're going to have square roots that, for the most part, can be simplified. You may get one in there that can't be, so realize that's a possibility. If I give you the square root of 5 and say simplify it, well, 5 is prime, so you can only split it up into 1 and 5, which means you're just going to end up right back at the principal square root of 5. It doesn't really simplify. So that could happen, but it shouldn't. If it happens at all in the homework, it shouldn't happen very often. Just keep in mind that not all of them can be simplified, but some of them can.